So basically in this problem, in this figure, ABCD is a rectangle and EFGH is a parallelogram. Using the measurements given in the figure, what is the length D of a segment that is perpendicular to HE and FG? So let's just mark 90-degree angles. So this random segment, what is a segment really has to do with anything? Well, the only thing we really know is that it's an altitude and this forms a 90-degree angle. And I gave a hint over here to find the area in two different ways. And the reason we do this is because we have this height, right? We have this altitude. So the altitude forms a 90-degree angle with the base. So the only thing we really know about the altitude is that the area of this parallelogram, so area, I'm not sure why I wrote EACF, it should just be EFGH. It's the same thing essentially, but I'll just make it more clear to make it consistent. The area of EFGH is equal to the altitude of so the area of a parallelogram, or actually before I even get there, what we can do is we can find the length HE. So does anyone know what the length HE will be? HE is, this is a 90-degree angle, this is 90 degrees, this is 90, this is also 90. So we know that HE, from here to here, HE is going to be the same as FG. Right? Because they're the same, they're both hypotenuses of a right triangle with legs of 3 and 4. So EH is the same as FG. Same thing, HG is the same as EF, right? Because they're both just hypotenuses of a right triangle with legs of 6 and 5. So now we know that this is a parallelogram. And the area of a parallelogram is nothing but the base times the height. So what is this base HE? Well, if you remember from 2 classes ago, 3, 4, 5 is a right triangle. So 3, 4, 5. So HE is 5. So the area of this parallelogram is the base, 5, times the height, which is D. And that's it. The area of a parallelogram is just the base times the height. And then how else can we calculate the area of this parallelogram? By information that we know. So now we have this D, and now it's going to be equal to something else. So now we know the area. So now how can we find the rest of the areas? Well, a really easy way to do this is to find the area of each of these triangles. So what's the area of this first triangle here? That's just going to be 3 times 4 divided by 2, which is 6. The area of this triangle is just 6 times 5 divided by 2, right? Base times height divided by 2, which is 15. That's 15. This will also just be 3 times 4 divided by 2, which is also just going to be 6. And then the final area over here is just going to be 15, just like this triangle here. Just like the triangle I just marked, the HDG is also going to have the same area, right? 6 times 5 divided by 2. So now we know the areas of each of those 4 triangles. So the areas of each of those 4 triangles, what do they sum to? So the sum of the areas of all 4 triangles is, well, just to make it clear, I'll clear up some space here. This is 6, this is 15, this is 6, this is 15. Right? Because we just use the area formulas. So the sum of the areas of all 4 triangles is just 6 plus 15 plus 6 plus 15, which is 42. Okay, so if the sum of these areas of all the triangles is 42, what is the area of the whole rectangle? The area of the whole rectangle is just the base times the height. The base is just going to be 10, right? 4 plus 6. AE is 4, and EB is 6. And this height is just going to be 8, since AH is 3, and HD is 5. So AD is 8, AB is 10. The area of the rectangle is 8 times 10, or 80. So then what is the area of this inside parallelogram? Which is going to be 80 minus 42, right? Because 80 is the area of the whole shape, 42 is the area of the 4 triangles, and this comes out to be 38. And we also know that the area, this 5 times d is going to be 38. Because, right, 5 is the base, and d is the height of the parallelogram here. Now we know that 5 times d is 38. And this means that d is 7.6, because we just divide by 5 to both sides. And this just means, since we have 5d is 38, we just divide by 5 to both sides to get d is 7.6. Any questions on this problem? Okay, let's review the homework problems from this week. A unit hexagram is composed of a regular hexagon with a side length of 1 and its 6 equilateral triangle extensions. What is the ratio of the area of the extensions to the original hexagon? So what it's saying is that this hexagram shape, this whole star is kind of thing you can see here, has a hexagon in the middle, and then it's triangular extra parts. Right? So we have to find what is the ratio of the hexagon, of the inside hexagon, to the area of the extensions to the hexagon. If you remember from last class, we just divide up our hexagon into 6 equilateral triangles. That's a very important fact that we're going to be using today too. So you divide up the hexagon into 6 equilateral triangles, and then we know that, well, this area is the same as this area. Basically, each of these triangles is going to be the same as the triangle outside of it. So this area is the same as this area is the same as this area is the same as this area, so on. These kind of areas kind of all match up. So half of it is inside the hexagon, half of it is outside the hexagon. So overall, there are six of these equilateral triangles. The hexagon has 6 triangles, and the extensions also have 6 triangles. So the extensions also have 6 triangles, right? Because there are 6 of these parts, the 6 of these parts that are outside the hexagon. So the ratio is just 1 to 1. Any questions? Okay, let's try number 2. In the figure, the outer equilateral triangle has the area of 60, and the inner equilateral triangle has the area of 1. So this is 1, the inside one, and the whole thing is 60. And then the 3 other trapezoids are congruent. So these 3 trapezoids all have an area of x. They all have the same area, right? Since they are congruent. They all have the same area since they are congruent. And that means that we have 3x, the 3 trapezoids area, plus the area of the inside triangle is equal to the area of the outside triangle, which means that 3x is 16 minus 1, or 15. That means that x is 5. So the area of the trapezoid is just 5. Let's move on to number 3. So we have, in the square, we have AF is 2FE. So this is going to be, and then CD is 2DE. And we have to find the ratio of BFD to ABCD. So note here, we don't actually have to find the areas, just the ratios. So we know that AF is going to be 2 times FE. So let's just say that AF is 2x. And then FE is just going to be x. CD is 2DE. And right, it's a square, remember? It's a square. And that means that AE is going to be equal to EC. So this is also going to be 2x and x. Because ED, they have to be the same 2 times 1 ratio, 2 to 1 ratio. And the side lengths itself are equal. And then now what can we do? What is the area of BFD in terms of this x? Well, again, in order to find the area of BFD, this complicated shape on the inside, all we really have to find is the area of the big shape minus the area of the parts that we subtract. So this is 3x, this is 3x. And actually from here, even though I let it be 3x for now, you don't actually have to let it be equal to 3x. You can just assume it's going to be 3, instead of 3x? Because I just said 3x arbitrarily, but since we only have to find the ratios won't change whether we have xb1 or xb100, because it's just scaling up the whole figure, right? So when you scale up the whole figure, if you scale up the whole figure, the ratios of the area of the triangle to the square is going to remain the same. But of course, if that wasn't clear to you, you could just say it's x, and you would still get a correct answer by doing this method, because the x terms would cancel out. But for simplicity, you can just ignore the x and just assume it's 1 or 2 and 3. So you can just assume this is 3, assume this is 2, assume that's 1, and it would still give you the same thing. Because if maybe we double the dimensions, let's say, then the ratio is still going to be the same. Okay, so what is the area of ASB? So AFB has the area of 3 times 2 divided by 2, which is 3. BDC has an area of 3 times 2 divided by 2, which is 3 as well. And FED has an area of 1 times 1 divided by 2, which is just 1/2. The 1/2. So the sum of the areas of these 3 regions is just 6.5. Okay, so now what is the area of the whole square? 9. 3 times 3, right? The area of the whole square is 9. The area of these triangle parts that we don't want is 6.5. So the area of the triangle BDF is just 2.5. And now we're asked to find the ratio of BFD to ABCE. We just do 2.5 divided by 3 times 3, again 9, which is just going to be 5/18. And the key thing to realize from this problem is that whenever you have to find ratios of areas, when you don't know the side lengths, assume it can be any side length you want. Because if you imagine, if you scale it up, it's going to be the same thing. The ratios are still going to be the same. So are there any questions on this trick here that I used? Okay, let's move on to number 4. So we're asked to find the area of the shaded region. So for this problem, all we really had to do was subtract the area of these regions that we are not supposed to have. So all we really do is subtract the area of these regions. So I'll just mark in different color. So let's just say this is the red region. This can be the red region. This can be these regions. So what is the area of these red regions? Just 4, right? They're unit squares. 4 is the area of the red regions. And now let me mark the blue regions, these blue regions here. So what is the area of these blue regions? Well, the area of these blue regions, we can just take the height times the base. So the base is just going to be 3. The height is just going to be 2.5. Because this whole thing is 5, right? We're given it's a 5x5 grid. The whole length is 5, and the height of this triangle is just going to be half of it, so 2.5. And that actually means that the area of the shape, in the area of one of these triangles, the area of the triangle is just going to be 3 times 2.5 divided by 2, which is just going to be 15/4. And then, since we know that each of the things have an area of 15/4, the area of all 4 triangles is just 15/4 times 4, 15, because there are 4 of the triangles. So what is the total area of the blue and the red region? The blue regions have an area of 15, right? Each of the triangles has the area of 15/4. The red regions have an area of 4. So total, they have an area of 19, the parts that we don't want. And the area of the whole shape is just 25. 5 times 5, 25. Because it's a 5x5 grid, so the area of the big thing is just 25. And that means the area of the shaded region is just the area of the big thing, 25, minus the area of the blue and red parts, 19, which gives 6. So the area of all these shaded regions is just 6. It's just 6, the sum of all 4. Let's move on to number 5. So we're given that semicircles POQ and ROS pass through the center O. What is the ratio of the combined areas of the two semicircles to the area of O? So for this problem, we just say this is R. This will also be R. Then this will be R. Just say that's R2. We don't know what it is yet. But something we do know, we don't know that, look, Q is 1, 1, 1, right? Q is 1, 1. The origin is 0, 0. So the distance between Q and O is just going to be, well, we know it's 1. We don't even have to call it R. So we know that we go 1 up and 1 right. So we go 1 up here, and then we go 1 right to get to 1, 1. That's clear to everybody, hopefully. Because we just go 1 up, then 1 right. So we know that the radius of the semicircles are both 1, right? Okay, so now what? What is the area of both of these semicircles? Both of these semicircles? Well, the area of one of them is just pi r squared. Sorry, pi r squared, pi 1 squared divided by 2, because it's half of a circle. Well, it's half of a circle, so the area of it is just going to be the area of a circle divided by 2. But then there's 2 of the semicircles, so we multiply by 2. And we can cancel out the 2's, and we actually get pi. So pi is the area of both of the semicircles. And another way we can imagine that is we put the 2 semicircles together, and now we have a circle of radius 1, which has the area of pi. Okay, so another thing that we can see is that this is 1, that's 1, this is 90 degrees. We can actually just apply the Pythagorean Theorem. So if we apply the Pythagorean Theorem, we get that OQ is just square root of 2. So OQ is square root of 2, and square root of 2 is the radius of the big circle. And another way that I talked about last time was the 45, 45, 90. So you could also use that fact. We don't know that yet, but we'll discuss some similar techniques in this class. So we can just use the Pythagorean Theorem or 45, 45, 90 triangles. So if you use Pythagorean Theorem, it's just going to be square root of 1 squared plus 1 squared, which is the square root of 2. Okay, so now we know the radius of this big circle is square root of 2. So the area of this big circle is just square root of 2 squared pi, which is, well, these cancel, just 2 pi. So the ratios of the areas of the semicircle to the big circle is just pi over 2 pi, which is 1/2. So any questions on this problem or any of the other problems before that? Okay, let's move on to number 6. So we have a circle of radius 2, and it's cut into 4 arcs, and the 4 arcs form the star figure. We have to find the ratio of the area of the star figure to the area of the original circle. So we have this arcs. So whenever you see arcs that form some obscure shape, the number one thing we should do is construct a circle. So whenever you see some arc that's not actually part of a circle, the only thing we really know about arcs is that it's part of a circle. So let's try forming a circle maybe. So if you imagine forming the circle, if you imagine kind of finishing it up like that, we see that these all are going to be quarter circles, all of this. They're all quarter circles. So if they're all quarter circles, then the area of those 4 quarter circles, well, again, these are all 90 degrees, right? These are all 1/4 of a circle because it's 90 degrees out of 360. So it's just a quarter circle. And we can see that 4 quarter circles, you can construct them to form a big circle. We can kind of put them all together. So in order to find this area of this starred shape, let's just find the area of the big square and subtract the area of the 4 arcs. So again, there are 4 congruent arcs, so the radius is just going to be, this will just be 2. And same thing here, because it's the same arc. We just put it in a different orientations. So these will all be 2. And then we know the area of this circle is just going to be pi 2 squared, or 4 pi. The area of the start region is just going to be, well, 4 times 4 squared. So again, the side length is going to be 4, 2 plus 2. The side length of the square is 4. So the area of the big square is 4 times 4, or 16. And the area of these 4 circular pieces, you can imagine putting them all together, they form one big circle. So the area of the circles is just 2 squared pi, right? Again, it's the same thing as just one whole circle, or 4 pi. So if the area of the start region is just 16 minus 4 pi, and we're asked to find the ratio of it to the original circle. So 16 minus 4 pi divided by 4 pi, we simplify this to get 4 minus pi over pi, which is this. Any questions on any of the homework problems? Okay, let's move on to today's topic. So today we're going to be doing length. So for the last 2 weeks, we did area. Today's length. So find the perimeter of the shape below. Does anyone have any ideas of how we can do this? We already really know the length is, the height is 10 and the width is 22. Does anyone know how we can possibly even do this problem?
We could add back in the missing parts of the shape. So like, for example, where it says 22, there's a bit of a missing, there's a square.
So the trick to doing this is to notice that, well, we have these obscure corners cut from the middle. And we have this rectangle. We have almost rectangle. We have an almost rectangle. So we have something that's almost rectangle. So let's just see what happens if you draw the rectangle. Or are any of you guys talking right now? I'm not sure if I can hear.
Wait, can you hear me right now?
Can you re-speak? I might be able to hear you now. If you have any questions.
Can you hear me right now?
I think there's some issue. I toggled some wrong setting. Okay, so I'm not sure, but were there any questions on the homework that I didn't hear? Okay, so yeah, we're doing this question now. I think I can hear now. There's some issue with the setting. So we have this awkward shape with a height of 10, a base of 22. We can imagine the big rectangle that has a base of 22 and a height of 10. And what we notice is that the perimeter of this shape, so let me try to mark it out. So
the perimeter of the shape, I guess, like, because you just drew, because like, so basically what you did for like the top right corner is you added in 2 lines to basically fix the corner and make it part of a whole rectangle. So basically, like, even if you just remove those 2 lines, the perimeter will stay the same because you have that cut into the rectangle that pretty much doesn't change the length of the perimeter.
Yeah, that's exactly right, because the reason for that is we can imagine taking this segment here. The segment is going to have the same length as this segment. And then if you imagine this segment here, it's not very clear, sorry. So I'll just use red again. So this segment here is going to have the same length as this segment from here to here. And in addition, we can think about this from a different perspective. We can imagine something like, we can take this segment here to the same length as this segment over here. And then similarly, we can take some segment here. Oh, sorry, that's not very clear. Some segment here is going to have the same length as this segment over here.
So basically, the perimeter of the entire rectangle is the same as, it's the same before you add the extra segments to make it a whole rectangle as it was before you added the segments.
Yeah, the reason for that is, so basically whenever you have corner cuttings, the perimeter is always going to be the same as the rectangle without the corner cuttings. So like, because again, for this other corner, we have this green segment is equal to this green segment, and the 2 rect segments are equal. So we can see that the perimeters are equal. So the perimeter is just going to be 2 times, it's just going to be the perimeter of the rectangle, which is 2 times 10 plus 22, which is 2 times 32, or 64. Any questions on this? Okay, so now we're going to try an AMC8 problem that uses this strategy. There are actually 2 ways to do this. I'll explain the other method first. So we have a letter T being formed by 2 2x4 rectangles, and they're asked to find the perimeter of this T shape. So it's a 2x4 rectangle, so 2 by 4. This is also 2 by 4. So imagine that, or somebody asked, will the perimeter be the same even if the cutting isn't at the corner? No. The reason for this is, so let me explain. Let me just go draw here. So if you have a rectangle, if you have a rectangle, you take a cutting from the corner, like from the middle, like this, right? Then the perimeter is not going to be the same, because even though these lengths are equal, these lengths match up. There's an extra. There's these 2 lengths are extra. But when it's at the corner, the lengths match up because this is equal to this, or this is equal to this, and this is equal to this. But at the middle, even though these lengths match up, the other side ones don't match up. So that was a good question, but keep in mind that it only works for the corners. Okay, so continuing on with this problem. So imagine that they were not together. Imagine that they're just 2 separate rectangles. Then what is their perimeter? Well, the perimeter of one of the rectangles is just 2 times 2 plus 4. So that's just the perimeter of one of the rectangles, which is 2 times 6, or 12. And both of the rectangles are going to have a combined perimeter of 24. Right? Except now we're putting them together. So now not all the regions are going to be there. For example, this region, even though we counted it as part of the perimeter of the rectangle, it's actually not part of the perimeter of the shape, because it's an extra kind of. And same thing for the rectangle on top. That same length is being counted as part of the perimeter, even though it's not actually part of the perimeter. So we're overcounting those 2 segments. So in the first rectangle, we're overcounting that length of 2. We don't actually have a length of 2. And in the second rectangle, again, we're counting the length of 2 that's there, but we don't actually have it. Even though we're counting it, it's not there. So we subtract an additional 2. We get 20. So that's the first method. Any questions on that?
You could also just add back in the rectangles on the side, right?
Yeah, that's actually going to be the second method I was going to show. So the second method is that you extend this. You extend the side lengths. You extend these lengths. And what you do is you have this 2 and 4 thing, and this is also going to be 4. Because, right, these are parallel lengths, so this length from here to here is going to also be 4, since this is 4. Same thing here, this will also be 4 on this side. And also we know that this whole thing is 4. This whole thing is 4, so this whole thing from here to here is also 4. And now we just have a rectangle with length of 4 and a height of 4 plus 2. This is 2, so a height of 6. A total of 2 plus 4. So the perimeter of that is just 2 times 6 plus 4, which is just 20. So the perimeter of that is just 20. We got the same answer again. So any questions on any of the methods for this problem? Yes, this corner cutting trick can be useful. So make sure, it's also pretty simple. So whenever you have a corner cut, it will always be the same perimeter as the outside shape. Because again, these will match up. These will both match up and be the same. And same things here, these will both match up and be the same. And same thing on the other side. These will match up and be the same. And these will match up and be the same. That's why the corner cutting trick works. But make sure not to get confused. Somebody asked for the first method, why did you remove the 2 2's? Okay, so the reason for that is, remember originally we found so I'm going back to the first method here. So originally we found the perimeter of the two rectangles, both of the individual rectangles, but then we have to subtract this length here because that length is not actually part of the figure. You see, it's kind of in empty space. It's not actually a length. It's not actually part of the perimeter. So this length of 2, this has a length of 2 here because this is 2, too. This is 2, to be clear. That's 2, the red length. And we're actually counting it when we just find the perimeter of both. So imagine that there's the two figures separately like this, like they're a little bit spaced out. If it was find the total perimeter of this shape, it would just be 24. But now we're going to have them putting them together. So that no longer this region, no longer out of these, okay, that was not. So no longer these regions are being counted because we're putting them together. No longer these regions are being counted because you just kind of plop them together. So these regions that were originally there, that we originally had a length of 2 that were counted, are not there anymore. So that's why we have to subtract them. So is that clear? So if you imagine that we didn't have it, then we have the perimeter of 24, but now it's not there anymore for either of the two rectangles. Okay, good. So now we're going to move on to this next problem. This problem actually has a similar strategy. So we have AB is 8, area of the polygon is 52, AB is 8, BC is 9. We're asked to find what DE plus EF is. So I guess this is somewhat of an area problem, but let's see how we can solve it. So again, the area of this obscure polygon. So what do you think we can do here to make it a nice shape? What can we do here to make it something that we know how to deal with? It's very similar to the previous problems. You can actually just extend these lines, just like earlier, to form a rectangle. Except the thing here is the difference here is that the area is not going to be the same because now we don't have this region in the middle. So the area is not the same. The perimeter is. Okay, so the area of this polygon is 52. So the area, okay, what is the area of this big rectangle? The area of this big rectangle is 8 times 9. The area of the big rectangle is just 72, right? 8 times 9. Okay, so now what's the area of this part that we cut off? Well, in order to find the area, we have to find the height and the base. So now we know the area, so let's see how we can do from here. So if you see here that this is 5, and this whole thing is 9. So then we can see that this part is just going to be 9 minus 5, or 4. So this part is 4. This will also be 4 then, right? Okay, so now what about FE? What is FE? Do we even know what we don't even know what FE is. FE is just some random length. So what do we really know about it? So whenever you have a random length, or random anything for that matter, in any type of problem that you don't know how to deal with, a classic strategy is just to assign it a variable, maybe x. So then this length will also be x. Now what is the area of FED? It's just going to be x times 4, or 4x. So that's the area of the part that we cut off. So the area of the part that we cut off is going to be 4x. The area of the big thing is 72. We have that 72 minus 4x is 52. Because the area of this part is, we're given it's 52. We're given that the area is 52. So we can see that the area of the big thing minus the area of the part that we remove is just going to be 52. And now we just solve this. We do 72 minus 52 is 4x, or 20 is 4x, which means that x is 20 divided by 4, or 5. So x is 5. Now we need to find DE plus EF. Well, DE, we know DE is 4, and we know EF is just x, or 5. So DE plus EF is just D is for EF of X, which is we found to be 5. So it's just 9. Any questions? Okay, let's move on to the next problem. So in this problem, we have triangle ABC is an isosceles triangle. So AB is equal to BC. So AB is BC. So actually, I don't really want to mark it here, but hopefully you can all see that AB is BC. And point D is the midpoint of BC and AE. So these are both equal, and these parts are both equal. And if you don't already know what this line symbol means, by drawing a line on 2 points, they basically mean that BD is DC, and AE is equal to DE. They're equal. And we also know that ABC is isosceles, which means that and AB is BC. So we know that these are equal to, these pink segments are equal to. Okay, so now what can we do from here? Well, triangle ABD is congruent to triangle ECD. So triangle ABD is congruent to triangle ECD. So ECD. And what does that mean, really? Well, we're asked to find the length of BD. We know that CE is 11 units long. So we know CE is 11, right? But we know that ABD and ECD are congruent. So if EC is 11, BA is also 11. Because we're given that congruent. ABD is congruent. So we know that they're congruent. And if AB is 11, then BC is 11, right? AB is equal to BC. We know AB is 11, so we know 11 is AB. So that means BC has to also be 11. So now we know BC is 11. And we also know that BD, so BD plus DC is 11, right? Because we have that. So BD plus DC is equal to 11. But then we know that BD is DC. Because D is the midpoint of DC. D is the midpoint of that. So BD, it has to be equal to DC. So now we can just say that this is just BD plus DC, but DC is equal to BD. So BD plus BD, it's 11. Or 2 times BD, it's 11. Which means that BD is just 5.5, or 11 over 2. So either of these answers would be okay. But in the AMC, you get option choices, so then you could just see which one would actually be that answer. Any questions? Okay, let's move on to this perimeter of a trapezoid problem. So what is the perimeter of trapezoid ABCD? Okay. So does anyone know what do you think the first step is? We know B is 24, we know AB is 30. The only thing we don't know is AD. We know everything else besides AD. So somehow we had to find AD.
First we could just cut off like the side CD. We could cut off a bit of the quadrilateral BCDE so that it's a rectangle and a right triangle.
Yeah, so we can do something along those lines. So we can just say that ABE is a right triangle. So we know that we can just find AE using the Pythagorean theorem, or we can also use other methods. So actually, I'm going to give you a minute or two to try to solve this on your own. So a hint is to also consider the altitude on C to AD. So this is a trapezoid. So try to find AE using Pythagorean theorem, and then try to do something to find the side length AD somehow. So I'll give you some time to try to solve it. So we can find AE using the Pythagorean theorem or Pythagorean triplet. I think we should actually move on because we have many more problems to cover. So this is ABE is a 3, 4, 5 triangle. So ABE is a 3, 4, 5 triangle. The reason for this is, okay, so whenever you see these kind of side lengths, the thing that you should do is you should look for the ratios of the side lengths. So the ratio of 30 to 24 is 5 to 3. Sorry, not 5 to 3. 5 to 4. Ratio is 5 to 4. And 5 to 4 is, if you remember from the 3, 4, 5 triangle, it's just going to be a 3, 4, 5 triangle, except amplitude. So it's going to be the same ratios, except if you remember from 2 classes ago, we discussed the trick for if 3, 4, 5 is a Pythagorean triplet, we can also have 18, 24, 30 be a Pythagorean triplet, since we just multiply by 6. That means that AE is 18. So we can just use that, okay, if this has a ratio of 5 to 4, then AE will be the 3 side length of the 3, 4, 5. So it's just going to have a length of 3 times 6 or 18. And don't worry about this Pythagorean triplet stuff too much. As long as you know how to just apply the Pythagorean theorem, you can just do 30 squared minus 24 squared. You could also just do this method. So and then you'd also get the same thing. But this is just a quicker way, and I just wanted to share that. And now we can do something similar. C to the altitude is 24. So that's 24. And does anyone remember what Pythagorean triplet has 24 and 25 in it?
7, 24, 25.
Yeah, so that's why it's important to have your Pythagorean triplets memorized. And if you don't remember, you can review the document or video from the classes. So 7, 24, 25 is a Pythagorean triplet. So that means this length is 7. And now we know that BC is 50. That also means that this is 50. So AE is this. And now what is the length AD? And if you remember from the beginning, AD is kind of like our unknown length here.
AD?
Yeah, because we don't know what AD is. We know all the other side lengths. We know what AB is. We know what BC is. We know what CD is.
AD is 75.
Yeah, now we can figure it out by these 3 parts. So just 18 plus 50 plus 7. Which is 18 plus 7 is 25. 25 plus 50 is 75. And now we just do, since this is 75, we can just do 30. The perimeter, which is 30 plus 50 plus 25 plus 75, which is just going to be 180. Any questions? Okay, let's move on to the next problem. Angle ABC of triangle ABC is a right triangle. So this is a right. ABC are the diameters of a semicircle. So the area of the semicircle AB is 8 pi. The area of the semicircle on AC is 8.5 pi. And rest on the radius of the semicircle BC. Okay, so how can we do from here?
8.5 is the hypotenuse. So basically, you have 8 pi and you have 8.5 pi. You can cancel out the pi because that will just make the scale just pi times smaller. So you could just get rid of the pi. Then you could use the Pythagorean theorem because you have one side, the length of one leg, which is 8. You don't know the length of the other leg, but you know the length of the hypotenuse is 8.5. So from there, if you solve for the length of BC and divide that by 2, you should get the answer.
Yeah, so that we can do something, you should do something like that. So we know the area of AB semicircle is 8 pi. That means that pi r squared divided by 2 is 8 pi, right? And that means that pi r squared, sorry, I didn't get this. So pi r squared is just going to be 16 pi. That means r squared is 16, or r is 4. In this case, we have the radius from this just going to be 4. So the whole length, AB as a whole is going to be 8. So AB as a whole is going to be 8. And what about for BC? Or sorry, for AC? we have the arc. Be careful here, wording. The arc on the semicircle has length, not area, 8.5. So 2 pi r divided by 2 is 8.5 pi.
Oh, okay, I missed the arc.
Yeah, so that, make sure to be careful about what's actually in the problem. So 2 pi r is 17 pi. And that means r is just 8.5. And if the radius is 8.5, the AC is just going to be 17. So AB has a length of 8, AC has a length of 17, and if you remember the 8, 15, 17 is a Pythagorean triplet, so BC is 15. And that means the radius of BC is just 15 divided by 2. Since BC is the diameter, which is 7.5. Any questions? Okay, so now let's try this last problem for length. A square, this is actually a really interesting problem. A square with side length 2 and a circle share the same center. The total area of the regions that are inside the circle and outside the square are equal to the total area of the regions outside the circle and inside the square. What is the radius of the circle? So this is a bit confusing. So the total area of the regions inside the circle but outside the square. So inside the circle but outside the square. That's going to be this region here. Because it's inside the circle but outside the square. And same thing, the area of the circle outside the circle but inside the square. So this region. So the blue and red regions are equal. Even though they may not look equal, don't judge a diagram that's always going to be 2 scale. These blue and red regions are equal. We have to find the radius of the circle. So let's just say the area of this white region in the middle is x, has the area of x, okay? And let's just say the area of the red region. So the red region has the total red region. So all 4 red parts have an area of y. So all 4 red parts combined have area of y. And let's just say that all 4 blue parts combined have area of y too, right? Because all 4 blue parts are going to be the same area as all 4 red parts. So they're going to both be y. The red part's y, the blue part's y. And the inside is just common, so well, that's just x. So the area of the square, so the square area is just going to be the inside part plus the area of the blue region, which is y. So the inside part is x, the blue region on the outside is y. The circle is going to be, well, the inside is x, and the outside again is just y. So the circle also has the area of x plus y. And that means the areas of the circle and the square are equal. So now we know the area of the circle is equal to the area of the square. So does that make sense to everybody? Because the area of the regions outside the circle, the inside region is common and the outside regions are both equal. So the areas combined are both equal. That was a really cool trick in this problem. And now the rest of the problem isn't that bad. The area of the square is equal to the area of the circle. So 2 times 2, the area of the square is equal to pi r squared. And now we just have to find r. This means that 4 is pi r squared, or r squared is 4 divided by pi. That means that r is the square root of 4 divided by pi. Any questions?
Wait, so basically instead of just writing, is that an answer option, like the square root 4 over pi?
Yeah, if it, in the real MC, you would have that as option.
Okay, because you could just write like 2 over the square root of pi, right?
Yeah, you could. It depends. You would have to see the option choices, and then you could see which one was equal in the real MC. So
okay.
So any questions? Other questions? Okay, so now we're going to do angle chasing. So most of you probably already know this, but the sum of the angles in a triangle is 180 degrees, and there are 360 degrees in a circle. And another less well-known property is that triangles with 2 angles equal will have the course. Okay, let me just explain in the diagram. So basically, if you have 2 angles equal like that, then that means these side lengths will have to be equal. These blue side lengths have to be equal if those 2 angles are equal. But if both of those side lengths are equal, So if these are both equal side lengths, then the angles have to be equal. So basically, in a problem, if they give you the two side lengths are equal, the angles have to be equal. Or if they give you the angles are equal, the side lengths are equal. So basically, if one is true, the other has to be true. Any questions on that? Okay, let's try a couple of examples. So in quadrilateral ABCD, this is somewhat of a, so AB and BC have a length of 10, CD and DA have a length of 17, and ADC is 60 degrees. Okay, so this is about 10, that's 60. We have 80, and so we know CD and DA are both 17. We have to find what AC is. And this is actually a kind of a troll problem because this information is irrelevant, it doesn't matter. And I'll explain why in a minute. These are both 17. That means that these angles are both equal, right? Because remember from this property, if the side lengths are equal, the angles are equal. And that means we have 2x plus 60 is 180, or 2x is 120, which means that x is 60. These are both 60 degrees. These are not x, they're x, but they're both equal and 60 degrees. And that means it's an equilateral triangle. And that means that AC is 17. And this is actually kind of a troll problem because this AB 10, those 10 lengths are kind of irrelevant. And when I first solved this problem, I also got my answers wrong because I was like, I didn't have to use this 10 at all. But just be careful here, and sometimes AMC will have these kinds of problems. But it turned out to be a pretty simple problem. The answer is just 17. Any questions? Okay, let's move on to the next problem. This is a little bit harder problem. So we have ABC. D is a point on side AC such that BD is DC. These two lengths are equal. And BCD is 70 degrees. So if BCD is 70, if this angle is 70, this angle has to also be 70, right? If you remember from the property, that's the same property. If the side lengths are equal, the angles have to be equal. This is 70 there. And that means that, well, this angle BDC, this angle here, that angle is just going to be equal to 180 minus 70 minus 70, which is 40. So this is 40 degrees here. And if BDC is 40, we have to find what ADB is. So ADB is this angle here. And ADB and BDC, which is 40 degrees, are supplementary angles because they're both on a line, and a line is 180 degrees. So a line is 180 degrees. So ADB plus 40 is 180. That means ADB is just 180 minus 40, which is 140. So ADB is 140 degrees, which is our answer. Any questions? Okay, so now we're going to try this final problem for today. The circumference of the circle with center O is divided into 12 equal arcs, marked A through L. What's the number of degrees in the angles X and Y? So for this problem, we see that it's divided into 12 equal arcs. So each of these arcs, so since there's 360 degrees in a circle, each of these arcs will have a length of 30 degrees. Or actually, that may be confusing, so I won't actually do it that way. So what is the measure of angle AOB, this angle? How big is that angle? Well, this angle it includes 4 parts. It includes 1, 2, 3, 4 parts out of 12 parts. So it includes 4 parts out of 12 parts of the whole circle, which is 360 degrees. So it includes 4/12 of 360 degrees, AOB, which is just 1/3 times 360, or 120 degrees. So AOE is 120 degrees, right? Now, well, if you remember, this is going to be R. This will also be R, because the radius of the circle is going to be the same. And same thing for these sides. They're both R. And if they're both R, we know that if the side lengths are equal, the angles are equal. And that means that this is also X. And what does that mean? That means, well, 2X plus 120 is 180, or 2X is 180 minus 120, which is 60. And this means that X is 30. That means that X is 30. These are both 30 degrees. So now you find the value of X. Now let's find the value of Y. Okay, so what is the measure of angle IOG, this angle? The measure of this angle is just going to be, well, we have 2 parts out of 12 parts, so it's just going to be 2/12 of 360, right? Because 2 out of 12 times 360, which is 60 degrees. This is 60 degrees. And then again, if you remember from the problem that we did here, if one is 60 degrees, we can just recalculate it, but I'm not going to do the same recalculations. If this is 60 and these are both the same angle, they have to also be both 360. So that these are both 60. And I won't do the same recalculations again, but you can just do that 2y plus 60 is 180. You could just solve that and you get y is 60. We already did that earlier, so I won't do it again. So that means y is 60, x is 30, so x plus y, the sum is just 60 plus 30, or 90. So any questions on this problem, or any other problems from this class? And again, the key ideas here was see that the R radius is going to be equal throughout the whole circle. And then we see that, oh, this is an isosceles triangle. This is also an isosceles triangle. And then we see the angles are equal. And then we can easily find x and y. And then we can just sum them. So any questions then? If they're okay. Okay, so then thank you for coming to all these classes. Later in a few weeks, I'll also planning on running a more advanced AMC 8 class, which will cover some more interesting and advanced AMC 8 problems and other problems too. So if you're interested in that, I'll send out the emails in a few weeks once I'm ready. So I'll send you the info for that class so you can attend it if you were interested. And thank you all for coming to all of these classes. And hopefully see you in the future in the other class. Okay, thanks everyone.
Thank you. Goodbye.
Thank you. Bye.
Bye. Thank you so much.